We kept the best for the last, so everybody who is here, listen carefully. This is Avantika Agarwal from the University of Waterloo. She will be telling us oracle separations for quantum classical polynomial hierarchy. The floor is yours.
Hello everyone, I am Avantika Agarwal. Today I will be talking about oracle separations for a quantum classical variant of the polynomial hierarchy. This talk is based on joint work with my advisor, Professor Shalev Ben-David. I will start by talking about the classical polynomial hierarchy, and then I'll introduce the quantum classical variant. So the classical polynomial hierarchy is an infinite hierarchy of classes whose 0th and first levels are the well-known complexity classes P and NP. For this talk, we'll think of P as follows. So suppose you have a judge, which is an efficient classical computer, and this judge is trying to solve some yes-no problem. So this judge gets some input x, it performs some efficient classical computation, and outputs yes or no. And we'll think of NP as follows. Again, we have this judge, which is an efficient classical computer, and now we have a debater dy, whose aim is to always try and convince this judge to say yes. Now together, they are trying to solve some yes-no problem. So they get some input x, and if this x is a yes input, then we want that the debater succeeds. So we want that dy can send some message m1 to the judge such that the judge outputs yes. On the other hand, if x is a no input, then we want that this debater does not succeed. So we want that no matter what message this debater sends, the judge always outputs no. Now, instead of considering this dy with the motive of convincing this judge to say yes, we could have considered a different debater dn, whose aim is to always try and convince the judge to say no. This gives us a different complexity class called co-NP, and the setup is the following. So again, we have this efficient classical judge, and we have this debater dn who's trying to convince the judge to say no. So if this input x is a yes input, then we want dn to fail. So we want that no matter what message this dn sends to the judge always outputs yes. And if this x is a no input, then we want dn to succeed. So we want that there exists some message m that the dn can send such that the judge outputs no. Now, we call these dy and dn debaters for a reason. And instead of considering these one-round protocols where only one of these debaters speak, we can start to think about problems which can be solved by using an I-round debate between these two debaters. This gives us the ith level of the polynomial hierarchy. So we have these two debaters dy and dn who are engaging in an I-round debate, at the end of which the judge makes a decision. For this debate, we have two choices of which debater speaks first, and this gives us two different complexity classes. So if dy speaks first, then we get the complexity class sigma I, and if dn speaks first, then we get the complexity class pi I. Together, sigma I and pi I form the ith level of the polynomial hierarchy. And now we can define our polynomial hierarchy. So the 0th level is P, the first level is NP and co-NP, the second level is sigma 2 and pi 2, and so on. And just like we believe that P is not equal to NP, we also believe that all of this polynomial hierarchy is infinite, all these classes are distinct. And this seems reasonable to believe because if we are allowed more rounds of debate, we should be able to use it to solve more problems. And we also get further evidence for this by the collapse property of polynomial hierarchy. So what does this property say? It says that if P is equal to NP, then all of the polynomial hierarchy collapses to P. More generally, if any two complexity classes in this diagram become equal, then all of the classes above that become equal to this particular class. So what is this telling us? This is saying that maybe it's possible that 5 and 6 rounds of debate have the same power, but then you can use this collapse property to conclude that 5 rounds of debate and 500 rounds of debate also have the same power. And that we should find a bit hard to believe. So the collapse property gives us some evidence to believe that pH is infinite. But now can we actually show such a result? So can we show that pH is infinite? So as it turns out, we also don't know how to show that P is not equal to NP, so we don't know how to show that pH is infinite. However, in the oracle model, we can show that pH is infinite. So I'll start by talking about what the oracle model is, and then I'll tell what results we can show there. So what is the oracle model? In the oracle model, all the classical computers that we have, they are given some additional power. So they are given the power to compute some function f for unit cost. So think of this classical computer M. It gets some input x. It performs some classical computation. During its computation, it can send queries y to this oracle f, and it can get the response f of y in a single time step. So it does not have to spend time to compute this function f. And maybe that helps this machine to solve some more problems. Now, in this model, we can again start defining complexity classes. So for example, if this machine M computes some function g in polynomial time, then we say that this function g belongs to the complexity class P with oracle access to f. So now in this model, what does pH look like? So we look at sigma I, and we want to see what sigma I looks like with the oracle f. So again, we'll have this efficient classical judge, and we have these two debaters dy and dn. And now in the oracle model, this judge is given oracle access to this function f. So on seeing the debate between the debaters, the judge performs some computation, and in between it can ask these questions to this oracle f to output a yes/no answer. So now can we ask whether pH is infinite in this oracle model? So is there some oracle such that pH is infinite? So in 1975, Baker, Gill, and Soloway showed that there exists an oracle such that P is not equal to NP. So at least in some oracle world, P is different from NP. And then it was an open problem whether there exists an oracle O such that all of pH is infinite. This problem was resolved in 1986 by Hostad, who said that yes, there exists an oracle such that pH is infinite. So there exists an oracle such that for every level I, there is something that the I plus 1th level of pH can do that the ith level of pH cannot do. But both of these oracle separations, they use a lot of structure in this oracle to be able to show such a result. So these are very contrived structured oracles constructed precisely for the purpose of showing that pH is infinite. And then it's natural to ask whether we need all this structure in the oracle to show such a result, or whether we can also show that pH is infinite even if you have some very unstructured oracle. So what do we mean by an unstructured oracle? Well, we'll talk about the random oracle model as our model of unstructured oracles. So what is the random oracle model? You have this classical computer M, and now it is given oracle access to a random function f. So what do I mean by that? On every query that this machine makes to this oracle, the function f outputs a 0 or 1 value uniformly at random. Of course, if you repeat a query, you'll get back the same response, but all the outputs of this function are 0 or 1 uniformly at random. So, and now it's easy to see that this oracle does not have any structure related to P or NP or polynomial hierarchy or any other complexity class. So now in the random oracle model, can we show that pH is infinite? This was an open problem in Johann Hostad's work from 1986. And it was resolved relatively recently in 2017 by Hostad, Rossmann, Servideo, and Tan, who showed that with probability 1, pH is infinite relative to a random oracle. So with probability 1 relative to a random oracle, for every level I, there is something that the I plus 1th level of pH can do that the ith level of pH cannot do. So this is all I wanted to talk about for oracle separations for pH. And now I'll talk about the quantum classical variant. But before I do that, one word of caution. While these oracle separations help us understand the structure of polynomial hierarchy and these complexity classes better, they should not really be taken as evidence to believe that pH is infinite in the standard model. For example, oracle separations between BPP and BQP have been known for a while. So oracles such that BQP is more powerful than BPP. However, it could still very well be possible that in the standard model, BPP and BQP are the same complexity class. So now I'll talk about the quantum classical variant, and we'll see what we can show there. So let's first start by defining it, and in particular, let's start by looking at a quantum analog of NP. So recall what was NP? NP was this class where we had this efficient classical judge and a debater who was trying to convince the judge to say yes by sending classical messages. Now, if we want to define a quantum analog, there are two things that we can make quantum. One, we can replace the judge with a quantum judge. Two, we can replace the message with a quantum message. For this talk, we'll let the message remain classical, and we'll replace the classical judge with a quantum judge, which gives us the complexity class QCMA, or quantum classical Merlin-Arthur. So this forms the first level of quantum classical pH, and the setup is just that we have an efficient quantum judge and this debater dy who is trying to convince the judge to say yes by sending classical messages. Now, similar to how we define the ith level of pH, we can define the ith level of the quantum classical polynomial hierarchy by considering an I-round debate between two debaters dy and dn. So we have an efficient quantum judge and two debaters dy and dn who engage in an I-round debate, at the end of which this quantum judge makes some decision. Again, depending on which debater speaks first, we get two different complexity classes. If dy speaks first, we get QC sigma I, quantum classical sigma I. If dn speaks first, we get QC pi I. And now we can define QCPH very similarly to how we define pH. So the 0th level is BQP, the class of efficient quantum algorithms. The first level is QCMA and co-QCMA. The second level is QC sigma 2 and QC pi 2 and so on. And we can also see a bit of how QCPH and pH are related. In particular, we can see that the ith level of pH is contained in the ith level of QCPH, because an efficient quantum judge can always just choose not to use its quantumness and just perform an efficient classical computation. In addition, we can also show a collapse property for QCPH. So in particular, we can show that if BQP is equal to QCMA, then all of QCPH collapses to BQP, and more generally, if any two classes in this left side hierarchy become equal, then all of the classes above that become equal to this class. So now that we have this definition of QCPH and we somewhat understand its relation to pH, it's natural to ask whether we can show that QCPH is also infinite in the oracle model. So we can ask whether there exists an oracle O such that QCPH relative to O is infinite. And if we can indeed get such a result, then it's also natural to ask whether we need a very structured oracle, or can we also show a similar result relative to a random oracle. So just for completeness, what does QCPH with an oracle look like? So recall we had this quantum judge and these two debaters dy and dn, and again this quantum judge is now given oracle access to the function f. Note that because this is a quantum judge, it has quantum oracle access to the function f, and in particular, it can make superposition queries to this function f. And now we want to see whether we can show something about this class in the oracle model. So this brings me to our results. We show that with probability 1, relative to a random oracle O, QCPH is infinite. So relative to a random oracle, for every level I of QCPH, there is something that the I plus 1th level of QCPH can do that the ith level of QCPH cannot. Second, we show that relative to a random oracle, no fixed level of QCPH contains all of classical pH. So what do I mean by that? Recall this diagram from earlier. So we saw that the ith level of pH is contained in the ith level of QCPH. But what about the I plus 1th level of pH? Is that also contained in the ith level of QCPH? So we show that relative to a random oracle, this is not the case. So for every level I, there is something that the I plus 1th level of pH can do that the ith level of QCPH cannot do. So now I'll talk a bit about the proof of this result. And once again, I'll start by talking about how you show such results in the classical setting. And then I'll talk about how we show this result for QCPH. So we want to talk about how to show oracle separations for pH. In 1984, first Sipser and Sachs gave a connection between constructing oracle separations for pH and showing circuit lower bounds for constant depth circuits. So in their work, they say that if you can show strong enough circuit lower bounds for constant depth circuits, then here is a method to use that to construct oracle separations for polynomial hierarchy. I'll not talk about how they get this connection, but I'll tell you what the connection is. So suppose you have some sigma I protocol, and you want to say that something is hard for this sigma I protocol. Then FSS 84 in their work convert this protocol to a depth I classical circuit with AND, OR, and NOT gates. And then using their work, if you can show that some function is hard for depth I classical circuits, then you can also construct a problem that is hard for sigma I in the oracle model. So now we can forget about sigma I and debaters and judges and protocols, and we can just focus on showing circuit lower bounds for constant depth circuits. So then how do you show that something is hard for constant depth circuits? One method to do that is the random restriction method, which says that after applying a random restriction, a constant depth circuit simplifies. So there are two things I need to explain here. One, what is a random restriction? And two, what do I mean by a constant depth circuit simplifying? So let's start by looking at restrictions. So what is the restriction of a function? So suppose you have some function f which takes an input x and outputs f of x. Then a restriction row of this function sets some input bits of this function to 0 or 1 value. So it restricts some input bits of the function to 0 or 1 values. And now the restricted function f sub row, it takes a smaller input x, sends those input bits to the unrestricted input bits for the larger function f, and evaluates this function f to get f sub row of x. So now that we know what restrictions are, what is a random restriction? Strictly speaking, a random restriction is any random distribution of your choice on these arbitrary restrictions that we discussed. However, we'll be interested in a particular kind of random restriction. So how do we sample these? So suppose you have this function f which you want to restrict. It takes some n-bit input x. Then we sample this n-bit input x from some distribution d. Then for every input of this function f, we choose to leave it unrestricted with probability p, and we restrict it to x sub I with probability 1 minus p, where x was this input string that we had just sampled from the distribution d. So then how can we use these random restrictions to show circuit lower bounds? These kinds of results are called switching lemmas in classical complexity. And in 1986, Hofstad in his switching lemma showed that suppose you have a DNF which is trying to compute some function f, then if you apply a random restriction to this DNF, then with very high probability over the choice of restrictions, your DNF becomes a small depth decision tree. But we know that small depth decision trees are a very weak model of computation, and there are many functions which they cannot compute. So now we can use this to show that some function is hard for DNFs. Think of, for example, the parity function. So suppose you have some small width DNF which is claiming to compute the parity function. Then if you apply a random restriction, then by the switching lemma, with very high probability, your DNF becomes a small depth decision tree. But we know how to show that small depth decision trees cannot compute parity function, which means that the original DNF could not have been computing the parity function either. And so now using this technique, you can show circuit lower bounds for more general constant depth circuits. So now what do we do in the quantum classical setting? So again, we'll follow a similar method. We want to reduce the problem of showing oracle separations to the problem of showing circuit lower bounds. So we look at a QC sigma I protocol. And again, using the FSS 84 connection, we'll convert this QC sigma I protocol to a slightly different type of circuit. So what does the circuit look like? We'll have a depth I classical circuit with AND and OR gates. And now this circuit will be followed by a layer of quantum query algorithms. So where do these quantum query algorithms come from? They come from the fact that the judge is now a quantum judge instead of a classical judge. And now using the connection from FSS 84, we just want to show circuit lower bounds for this class of circuits. So we just want to show that some function is hard for these circuits. And this brings me to our main technical result. We show a switching lemma for quantum query algorithms to help establish that certain functions are hard to compute for this class of circuits. So what does our switching lemma say? Suppose you have some quantum query algorithm and you apply a random restriction to its input bits, then with very high probability under the choice of random restriction, your function will become very close to a small depth decision tree. Note that there is one difference from the classical setting. Now this decision tree will make an error on some inputs. However, if your input distribution is a product distribution, then this fraction of inputs will be very small, regardless of what product distribution you pick. So this decision tree is making an error on a very small set of inputs. And now we can use this switching lemma to show circuit lower bounds for these QAC0 circuits that we discussed. And that gives us oracle separations for QCPH. In fact, our switching lemma says something slightly stronger. So it says that, in fact, our switching lemma works for low degree polynomials. So if you have some Boolean function f, which is being approximated to small error by some low degree polynomial, then our switching lemma says that under a random restriction, with very high probability, the function becomes close to a small depth decision tree. And as a corollary, it also works for quantum query algorithms. So that is all I have to say about our result, and now I'm happy to take any questions. Thank you for attending.
Thank you very much for the very clear introduction of the hierarchy and for the results. Questions?
Sounds very clear talk. I'm wondering, there's like a recent work, I think last year, they talk about like QCPH, but with a certificate, it's a distribution, and they're showing that it's equivalent between these two models. So I'm wondering, like this oracle separation result you just showed is extended to that setting, or there's some technical barrier?
Oh, I see. I haven't directly thought about it, but I think if you try to do this conversion from the QC sigma I protocol to these circuits, then you'll get some sort of distribution over circuits.
Okay.
And I think you should be able to use these switching lemma techniques to say that these circuits cannot compute hard functions. But I might need to check all the details to see if it works.
Thanks.
Thank you for the very clear explanations. I love the idea of a debater. Never thought of it that way before. I was wondering, where are you using the random oracle in the switching lemma?
Oh, I see. So the random oracle comes in from the fact, so if you just apply a switching lemma to say that there is a restriction such that this function will make such that this circuit will make an error, then you get that there exists an oracle such that something is hard for sigma I. If, however, your random restrictions, they give you an average case circuit lower bound. So if your random restriction completes to the uniform distribution and you say that the circuit will make an error on a large number of inputs, say close to half of the inputs under the uniform distribution, then that gives you a random oracle separation.
So I don't fully understand, but thank you.
So if I understand it correctly, the QCMA model, when you take logarithm on everything, then it reduces to it corresponds to the AC0 circuit, and each leaf is a quantum algorithm with polylog query time.
Polylog query complexity, yes.
So I wonder, so what's the correspondence? What's the corresponding model for QM? Let's say QMA. What will the middle of the tree look like?
So for QMA, you can't really have this like OR gate kind of circuits because the set of states, because you have an infinite set of states instead of a small number, instead of a small classical certificate. So in particular, this technique, with this technique, if you have classical certificates, then you're basically doing a union bound over all choices of fixing the classical certificates. This kind of union bound would not work if you have a QMA query algorithm. So we thought about whether our switching lemma will also work with QMA query algorithms instead of QCMA, and at least we could not make it work.
Okay, thank you.
Yeah.
I don't see any more questions, but I might ask, because it's a last talk. So you said we should take these claims with caution, right? That we shouldn't say that if we have separation in Oracle, we have separation between BPP and BQP. So what do you believe there? Do we have separation?
Well, I guess I would like to believe that indeed BQP is more powerful than BPP. But one more motivation for looking at these oracle separations is that they tell you whether, so any proof that separates BQP from BPP, that has to be a non-relativizing proof. So in that sense, these oracle separations at least tell you something about the proof technique that you can hope to use to separate BQP from BPP.
Okay, thank you very much. I think that's the best place to stop, and I thank everybody in this session too. Yeah, thanks.